Silicon now interfaces directly with living human tissue. Microelectrode arrays are capable of reading and writing electrical impulses from inside the brain's cortex. This projection maps the commercial expansion of neurotechnology, which is expected to grow from $9 billion today to over $28 billion by 2036. Industry leaders like Neuralink, Synchron, and Medtronic are moving these interfaces out of research labs and into mass-market commercial production. This shift creates a permanent link between the human nervous system and global digital networks. Linking millions of human brains to the internet changes the definition of a security breach. We are now defending the organic hardware of the mind. This is the medical cyber paradox. While these devices pass rigorous clinical safety reviews, they often reach the market with a significant built-in security gap. The engineering constraint is physical energy. Microbatteries powering these implants cannot handle the computational load of AES-256, the heavy encryption standard used in conventional IT. To compensate, manufacturers use unauthenticated over-the-air firmware updates. This creates a direct, unsecured pathway into the patient's brain. Brain data is the ultimate biometric. It is an immutable map of a person's physiological and psychological state. Unlike a password, once this data is exfiltrated, it is compromised permanently. Since traditional perimeter defenses cannot work inside human tissue, we must defend every stage of the architecture, from the individual neuron up to the cloud. This diagram identifies 7 distinct vulnerability nodes across the entire biodigital data pipeline. At node 1, the implant, a software intrusion manifests as a physical attack. An attacker only needs to manipulate operational parameters, like voltage or pulse frequency, while keeping them just below the system's safety alarm thresholds. This exploit mirrors Stuxnet. The top section shows a normal deep brain stimulation waveform. Below is a manipulated Stuxnet-style waveform. Altering the frequency induces neuronal flooding, sending chaotic signals that override natural patterns. This results in artificial seizures and irreversible tissue damage inside the brain. At the hardware layer, the digital exploit becomes a kinetic strike against human biology. The next vulnerabilities appear in the transport and local app layers, where the implant communicates with the smartphone. These connections often rely on unencrypted radio frequencies or contain Bluetooth flaws like knob and bluefrag, allowing an attacker to intercept or hijack the signal. Interception leads to data spoofing, where falsified telemetry data tricks automated medical systems into reacting with lethal force. This graphic details spoofing scenarios. In the top row, faking low blood sugar causes an insulin overdose. In the middle, spoofing cardiac telemetry forces unwarranted defibrillator shocks. At the bottom, disrupting EEG signals generates false diagnostics, leading to unnecessary psychotropic drug administration. By hijacking the transport layer, an attacker weaponizes the implant's own medical logic against the patient. The final stage of the pipeline reaches external Wi-Fi networks, vendor APIs, and third-party cloud databases. While the vulnerabilities here involve standard IT issues like exposed S3 buckets, the payload is the patient's entire neurological history. Once these datasets are breached, de-anonymization algorithms can link raw brain activity back to specific individuals. This enables mass neurosurveillance. State actors can analyze this telemetry to identify a person's psychological state or intent. This graphic details the legislative response, including the American Mind Act, which classifies neural data as a uniquely protected category under the law. A breach at the cloud layer commodifies fundamental human cognition. It is the mass exposure of a person's inner psychological state. Since perimeter defenses cannot protect a device inside the skull, security must be built directly into the silicon from the start. This architecture centers on a trusted execution environment, a physically isolated hardware enclave inside the device processor. Raw brain data enters the enclave on the left, where it is processed locally. Only sanitized, non-identifiable telemetry is allowed to exit on the right. Before transmission, the system applies differential privacy, injecting mathematical noise to ensure the data cannot be de-anonymized later. To bypass the energy limit, engineers use lightweight cryptography. Algorithms like ASCON secure the data without draining the implant's critical power supply. This strategy physically and cryptographically traps raw biological data inside the implant's processor. Zooming out, we see how this on-device protection integrates into a comprehensive four-layer security architecture. The transport layer must enforce zero-trust network segmentation and strict certificate pinning to block interception. The cloud layer requires data minimization and quantum-resistant encryption to protect patient privacy for decades. This technical stack requires the support of the bottom regulatory layer to mandate these protections across the entire industry. The window to implement these standards is closing. Millions of vulnerable devices are about to be mass-produced and permanently embedded in patients. As neurotechnology scales, the distinction between IT infrastructure and human biology vanishes. Securing the silicon is now the baseline for protecting the mind.